to find the values of n if the given quadratic equation 2n minus 1 times x squared plus n plus 1 times x plus 1 equals to 0 has two real roots. From the nature of roots, we know that for a quadratic equation having two real roots, the discriminant d, which is b squared minus 4ac, must be greater than 0. And from the given quadratic equation, a is 2n minus 1, which is the coefficient of x squared. B is n plus 1, which is the coefficient of x. And C is 1, the constant term. Thus, the discriminant d, which is b squared minus 4ac, will be n plus 1 all squared for b squared minus 4 multiplying 2n minus 1 for a multiplying 1 for c must be greater than 0. Opening up the brackets that we have here, n plus 1 squared expands as n squared plus 2n plus 1. Then the product of negative 4, 2n minus 1 and 1 will be minus 8n plus 4, and that is greater than 0. Combining the like terms, we have n squared plus 2n and minus 8n gives negative 6n, and 1 plus 4 gives plus 5, and that must be greater than 0. This gives us a quadratic inequality. So we first factor the left hand side, and the factors of plus 5 that we add up to negative 6 are negative 1 and negative 5. This quadratic inequality factor as n minus 1, n minus 5 is greater than 0. And for the product of two numbers to be greater than 0, there are two possible cases. The first case is when both factors are negative. That is, n minus 1 is less than 0 and n minus 5 is less than 0. If n minus 1 is less than 0, then it means n must be less than 1. And if n minus 5 is less than 0, it means n must be less than 5. Now, is it possible for n to be less than 1 and also less than 5 at the same time? Let us check it out with the original equation. So we're going to put OR here for now. To carry out this check, we are going to be testing a value that is less than 1 and then test a value that is less than 5 in order to see the validity of these solutions. First, let's check n equals to 0, which is less than 1, and see what it gives us in the original equation. Now with n equal to 0, the original equation, which is 2n minus 1x squared, 2n minus 1 becomes 2 times 0 minus 1, that's negative 1 times x squared, that's negative x squared. And n plus 1x will be 0 plus 1, which is 1, so that's positive x, and plus 1 equals to 0. Now testing with the discriminant again to see whether the result is valid, if this is actually going to have real roots. The discriminant d is b squared, the coefficient of x is 1, so that's 1 squared minus 4 times the coefficient of x squared is negative 1, and the coefficient, the constant term is 1. This gives us 1 plus 4, which is 5. Here d is greater than 0. What this means is that the solution n less than 1 is valid. Checking the second value, n is less than 5. Let us pick a value that is less than 5 but more than 1. Let's check 2. When we put n equals to 2 in the original equation, 2n minus 1 becomes 2 times 2 minus 1, that's 4 minus 1, 3x squared. Then 2 plus 1x, that's going to be plus 3x, and the constant term remains 1, equals to 0. Applying the discriminant again on the resulting quadratic equation, we have d to be b squared, that's 3 squared, minus 4 times 3 times 1, that's 4ac. And that is going to be 9 minus 12, which is negative 3. Now here d is less than 0. So at any value less than 5 but not less than 1, the solution is not valid. That means n less than 5 is not valid. However, we need to be very careful here because any value less than 1, as we have seen before, is valid. So we can put it this way, that 1 less than n less than 5 is not valid. Now this is the first case where we consider the two factors to be negative. Let's see the second case where the two factors are considered to be both positive. If the two factors are positive, what this simply means is that n minus 1 is greater than 0 and n minus 5 is greater than 0. And if n minus 1 is greater than 0, that means n is greater than 1. Or if n minus 5 is greater than 0, that means n is greater than 5. Again, can n be greater than 1 and greater than 5 at the same time? Let us test like we did during the first case. However, for n greater than 1, we have tried n equals to 2 during the first case. So we are going to go for n greater than 5. Now we check a value that is greater than 5. N equals to 6. When n equals to 6 and we put it into the original equation, 2n minus 1x squared becomes 2 times 6, 12 minus 1, that's 11x squared, plus n plus 1x, that would be 6 plus 1, which is plus 7x, and plus 1 equals to 0. Using the discriminant again, the discriminant d is going to be 7 squared minus 4 times 11 times 1, that's 4ac, and that gives 49 minus 44. In this case, d gives a positive 5, which means that d is greater than 0. What this tells us is that n is greater than 5 is a valid solution. Then, having seen the valid solution, we can state that the possible values of n will be n less than 1 and when n is greater than 5, excluding the values 1 less than or equal to n less than or equal to 5. So here is the solution. In the second one, we want to find the values of n for which the quadratic equation x squared plus n plus 2x plus n squared equals to 0 has equal roots. And if this has equal roots, then the discriminant d must be 0, where a is 1, the coefficient of x squared, b is n plus 2, and c is n squared. Thus, the discriminant d, which is b squared, n plus 2 squared, minus 4 times a, which is 1, times c, which is n squared, must be equal to 0. Opening the brackets, we have n squared plus 4n plus 4, and the product of 4, 1, and n squared is minus 4n squared, must be equal to 0 for this to have equal roots. Then n squared minus 4n squared gives negative 3n squared, then plus 4n plus 4 must be equal to 0. If we multiply through by negative 1, we are going to have 3n squared minus 4n minus 4 equals to 0. And 3 multiplying negative 4 is negative 12. The factors of negative 12 that will give negative 4 are positive 2 and negative 6. So we use this to expand the middle term to have 3n squared plus 2n minus 6n minus 4 equals to 0, giving us n from the first two groups factored out, 3n plus 2 left in the brackets, and from the second group we can factor negative 2, also leaving us with 3n plus 2 equals to 0. Now that 3n plus 2 is common, we factor it out, 3n plus 2, then multiplying n minus 2 must be equal to 0. And if this product is equal to 0, then 3n plus 2 must be 0, or n minus 2 is 0. If 3n plus 2 is 0, that means n must be negative 2 over 3. And when n minus 2 is 0, n must be 2. These are the values of n for which the given quadratic equation here have equal roots. Make sure you don't go yet and watch to the very end. There is one more for you. In the third one, we want to find the values of n for which this quadratic equation nx squared plus n plus 8x plus 9 equals to 0 has no real roots. And if it has no real roots, then the discriminant d must be less than 0, must be negative. To find the discriminant d, a is n, the coefficient of x squared, b is n plus 8, and c is 9. Putting this into the discriminant formula, b squared minus 4ac, we have the discriminant d to be n plus 8 squared minus 4 times n times 9. This must be less than 0. Opening the brackets up, we have n squared plus 16n plus 64 minus 36n being less than 0. And combining the like terms, we have n squared minus 20n plus 64 being less than 0, leaving us with yet another quadratic inequality. And the factors of 64 that add up to negative 20 are negative 4 and negative 16, meaning that the left hand side, the quadratic expression factors as n minus 4, n minus 16 less than 0. Here, when the product of two numbers is less than 0, there are also two possibilities. The first possibility is when the first one, n minus 4, is negative, that is less than 0, and the second one is positive, n minus 16 is greater than 0. If n minus 4 is less than 0, n must be less than 4, and for the second one, n must be greater than 16. Again, these being inequalities, we need to check for their validity. Now, to start our check, let's take a value less than 4. Let's take 3. So checking with n equals to 3 in the original equation, we have the original equation becoming 3x squared plus n plus 8 will be 3 plus 8, that's 11x plus 9 equals to 0. Now applying the discriminant on this again, we have the discriminant d to be 11 squared minus 4 times 3 times 9. And this gives 121 minus 108. This is 13, meaning that d is greater than 0. This has real roots, and as such, n less than 4 is not a valid solution. The other value is n greater than 16, so we are going to test with a value greater than 16 as well, say 17. Now checking with 17, the original equation becomes 17x squared, that's ns squared. Then 17 plus 8 gives 25, that's plus 25x and plus 9 being equal to 0. The discriminant again gives 25 squared, that's b squared, minus 4 times a, 17 times c, which is 9. This is 625 minus the product of 4, 17 and 9 is 612. This gives positive 13. Again, d is greater than 0. And with d greater than 0, that means n greater than 16 is also not a valid solution. This means that the very first case we are considering, n less than 4 and n greater than 16, do not provide any valid solution. Now on to the second situation. With the second case, we check when n minus 4 is greater than 0 and n minus 16 is less than 0. That is when the first is positive and the second is negative. In that case, n must be greater than 4 and n must be less than 16. This can be combined if we write 4 is less than n and n is less than 16, eventually combining as 4 less than n less than 16. However, before we go on, we can check these values too to see their validity. So first, let us consider a value that is greater than 4. Say 5. The original equation becomes 5x squared plus 5 plus 8x, giving 13x plus 9 must be equal to 0. And the discriminant d is 13 squared minus 4 times 5 times 9. That is 169 minus 180. This is negative 11. D is less than 0. D is negative, meaning that n greater than 4 is a valid solution. Then with the second value, let's check a value of n less than 16, say 15. When we put n equals to 15 in the original equation, it becomes 15x squared plus 23x plus 9 equals to 0. The discriminant again is d equals to 23 squared minus 4 times 15 times 9, where 23 squared is 529. And the other product for 15 and 9 is 540. Again, this is a negative value where d is equal to negative 11. That is, d is less than 0 or negative, meaning that n less than 16 is another valid solution. Therefore, the possible values of n lie in the range 4 less than n less than 16. We believe you have learned how to use the discriminants to find certain values for the different nature of roots of quadratic equations and how to use the same discriminants to test the validity of the solutions. Please leave your thoughts in the comments box, subscribe to this channel, and make sure you hit the notification bell so that you can be updated as to our math tutorials. You can also browse through this channel. You see loads of exciting tutorials.